I'm going to take you through the equilibrium constant, how to calculate it, and what it means. You'll need to complete these notes as we go through. Some I'll complete, and you need to complete the rest. So if you look at the definition of the equilibrium constant in your book, it says that it's controlled by the law of mass action, which will be written as your products raised to the power of their coefficient over your reactants raised to the power of their coefficient. So this expression will allow you to calculate not only the equilibrium constant, but all equilibrium concentrations. So looking at this reaction called the Haber process, looking at the graphs and running two different experiments, you can see that it didn't really matter where we started with how much concentration of reactant or product. We reached equilibrium at the same point where you have no net change in that equilibrium concentration. So think about this. When equilibrium has been achieved, is it true that these are equal? And be able to explain that. The law of mass action I just wrote for you up there. You can look at it in your textbook or recopy my at the top. So here's the equilibrium constant expression for the Haber process. Do this for the decomposition of hydrogen iodide into its elements. So write the equation and then write the equilibrium expression. On the back, we are now looking at what happens during an equilibrium process. So we've got a simple reaction of N2O4 going to 2NO2, equilibrium situation. We've got the initial concentrations of both reactants and products and the final concentration. Looking at where we started and where we ended, we can find the change in concentration under each of these scenarios. So go ahead, follow this pattern, and find that change through experiment number 5. So we're going to compare that change of NO2 with the change of N2O4. If you will look at all of those changes, you will see that the NO2 is twice that of N2O4 due to the 2-to-1 mole ratio. Again, when you write the equilibrium expression of that, that becomes a square effect. Raise the concentration to the power of the balanced equation. So now if we go in to our experiments and put in those equilibrium concentrations, so each of these have been brought forward from your previous work. If you put those in and follow the equilibrium expression, you will take your 1.40, square it, divide it by 9.30. Do this for all of them down the line. You should see within some experimental error that you have the constant, the equilibrium constant of 0.210. So what you're trying to prove to yourself is that the value of that constant at any given temperature, if you change that temperature, you will change that equilibrium constant. It doesn't depend on where you start your reaction. It simply depends on that ratio of reactants to products. So Kc, or just plain K, or KEQ, all deal with Ks that use the unit of molarity, moles per liter, and that is always shown with brackets. Pressure can also be a way to represent concentration, and that is Kp. There's still an equilibrium constant just with respect to pressure versus concentration. When your moles of gaseous products equal your moles of gaseous reactants, and we'll talk about this more, your Kc and your Kp are equivalent. Usually there are no units put down for K values. So looking through your notes, you want to understand why When K is much larger than 1, your equilibrium lies to the right, making your reaction product favored. And of course, in our last chapter, that means it's more thermodynamically favored with a negative delta G. When your K is much less than 1, your equilibrium lies to the left, meaning that you are reactant favored or non-thermodynamically favored. You can alter a reaction, and by changing that reaction, you will change the K value. So notice here we have a reaction, and here we have a doubling and a flipping of that reaction. The relationship is not the same as with Hess's law, where you would flip it and put a negative sign and double it. Here, when you flip it, it's the inverse of that. Okay? So actually, we haven't doubled it. I'm sorry, we just flipped it here. So here, the flipping of that is just the inverse of that K value. If this is the K going forward, then the K going reverse will be, if this is a small k, the reverse K will be larger. Very similar to your spontaneous delta G's. If they are spontaneous in the forward direction, they will be non-spontaneous in the reverse. So if you flip your reaction, it's the inverse or reciprocal of that K value. Answer these two questions based on the size of your K values. See if you can come up with an answer for that, and we'll discuss it in class. Here, we're looking at another change in our equation. So this one, we are keeping it going in the same direction, but we are doubling it. So instead of doubling that, we are squaring that K value. So if you double, or whatever power you change your equation by, you will raise that K value to that. So the relationship is your new K value will be your original raised to the power that you multiplied those coefficients by. So see if you can do this to these two equations. So here I have given you two K values. Write your equilibrium expressions and see if you can take these two equations and add them up to equal this equation and write its K expression. So this is the idea of adding up reactions to get a new reaction. But instead of adding up the K's, you will multiply those K's together. Okay? So I've given you the equilibrium constants for these so you would not have to look them up. To get this equilibrium constant, you will need to add up these reactions, change your K to whatever you needed to do, and then multiply them. We certainly will go over this one in class, but give that a try. Two more reactions to practice. So when you have equilibriums that have heterogeneous states of matter, you need to make sure, and we already talked about this in class when we talked about Le Chatelier, you do not include pure solids and pure liquids. They have no concentration values. The law of mass action deals with only concentration or pressure values. Solids certainly have to be in the reaction for the chemistry to occur, but their concentrations don't change. When you write a Kp expression, okay, it differs from a Kc or Keq in that instead of writing brackets, which always mean molarity, you simply write the symbol for pressure, just a large P. The K values can be expressed in either one of these units, but if you write pressure as a concentration, they will not give you any credit. So if you looked at this reaction over here, these solids would have been left out. So the only thing that controls that equilibrium expression is the pressure or concentration of CO2. So go ahead and write the K expressions for all of these, making sure that you leave out pure liquids and solids. See if you can explain how you're going to calculate the value of K if you have the concentration of all reactants and products. That's a pretty simple math to be able to do. That's your first level of equilibrium problems. So you've read a handout on ICE. So I stands for initial change equilibrium. We will always use ICE to solve our problems. We'll start with simple ones and build on those. So when you're doing an ICE problem, you will always write the balanced equation and put that at the heading of your ICE table. You will put your initial values down. If you're not given anything, they're assumed to be 0. Sometimes you're given an equilibrium amount, as you were in your handout, and you'll be able to figure out that change. Otherwise, you have to define that change in terms of X based on the stoichiometry of the reaction. So figure out what you would put down here for these equilibrium values and see if you can write the expression based on this. So here's the Kp expression. Show me that you know what you would put in to represent SO2, O2, and SO3. And again, making sure that you square those values. And we will go over this in class next time.